is Jinyang Yu of Tsinghua University of China, presenting a full paper entitled PrintShear, shear input based on fingerprint deformation. Thank you.
Thank you. Hello, everyone. I'm JINYANG Yu from Tsinghua University. Today is my honor to present you our work, PrintShear. This is a new shear input method based on fingerprint deformation. So most touch-based input devices, such as touchscreen and touchpads, capture low-resolution capacitive images when a finger touches the surface of the device. So these devices only output the 2D position of the contacting point, so which are insufficient for complex control tasks. So to expand the modality of touch input, researchers have proposed a variety of techniques, including shape and size of the touching area, force applied on the touching surface, and finger poses, and etc. So shear input refers to the use of force vector, which is parallel to the device surface as input. It has been studied by researchers to provide additional input modalities. However, most shear input techniques require additional sensors or attachments, which could affect the form factor of the mobile devices and bring extra cost. So thanks to the rapid development of under-screen fingerprint sensors, fingerprint images can be captured. Therefore, it becomes possible to use fingerprint images as a new input modality beyond user authentication. Different from low-resolution capacitive images, fingerprint images contains rich information about a finger, including clear ridges, minutiae, and touch area, and etc. So when a shear force is created by a finger, friction will cause the contacting area on the fingerprint to deform. Deformation in the center region is small, while that in the boundary region is significant. The image in the first row shows the deformation of the fingerprint under shear force. Images are created by taking differentials between the first image and the following form images. The images in the second row demonstrate three types of deformation: the lateral, longitudinal, and rotational. So this is the flow chart of our proposed method. So the user have to first register two finger regions to control rotation and translation separately. Then when the manipulation starts, the fingerprint scanner captures a continuous sequence of fingerprints. Feature points are extracted from the first frame of the fingerprint and matched with the registered regions. The matching score are calculated, and the finger contact area is determined based on the scores, which will log the degrees of freedom. So in each subsequent frame, feature points are extracted and matched with adjacent frames. Then the deformations are determined based on the relative position and distances between the matched point pairs. Leveraging the elastic property of the finger skin, the deformations are mapped to velocity control commands for 3 degrees of freedom. By combining the initial determined rotation or translation, 6 degrees of freedom control can be achieved. Based on the proportion of moving point pairs, finger actions are classified into 3 categories: pushing, static, and sliding. The images in the first row are push actions in longitudinal, lateral, and rotational directions. The image in the second row shows sliding and static actions, which are ignored in our study. So we conducted a finger deformation experiment and 4 3D object docking tasks to evaluate the feasibility and performance of PrintShear. We recruited 12 participants to complete the experiment. The deformation ranges for each finger and different regions in all 3 directions are shown here. When the data is grouped by fingers, the sum showed a better overall deformation ability than the index finger. And when the data are grouped by regions, the center region showed a better showed overall deformation, a better deformation ability than the other regions. This could be explained by the differences in touching area size where a large area has more potential to deform. We use a 3D T-port model for docking tasks due to the simple structure and clear indication of orientation. A timer will start when a participant makes the first movement using each input device and stopped when the angle difference in each axis is less than 2 degrees and the distance from the object to the target position is less than 2 pixels. And we compare the performance of 4 input methods in the docking task. Firstly, the PrintShear using a standalone fingerprint scanner, track point from a ThinkPad laptop, a touch screen from a Huawei laptop, and finally a space mouse. We divided the random position into 2 groups, a short distance group where the distance between the moving object and the target are less than 80 pixels, and the long distance group where the distance are between 80 to 300 pixels. The results are shown here in the violin plots. We can see that traditional touch input has the shortest completion time in both groups, but the difference is more obvious in the short distance group. We believe that this is due to the isotonic nature of conventional touch input, where actions are mapped to position control, but the performance degrades due to significant clutching in longer distance movements. And here, PrintShear has a similar completion time compared to track point in both distance groups. This is a demo of 2D translation task using PrintShear and track point. So in the 3D rotation task, PrintShear outperformed the other 2 methods. In the 6th degree of freedom docking task, PrintShear outperformed the other 2 methods. And however, significant differences are observed only when compared with the traditional touch input. The average completion time is 19.79% shorter. And there are 2 demos of PrintShear comparing with traditional touch input and the space mouse in 6 degrees of freedom docking task. So we also did the working load experiment. The workload results using NASA TLX show that the least overall workload has required by the PrintShear. It should be noted that the physical demand for PrintShear was the highest among all methods. This is reasonable since deformation is created by shear force, which requires a relatively large pressing force. And although PrintShear showed promising results, there are some limitations in our study. Firstly, fingerprint images were captured using a large standalone optical fingerprint scanner. Other form factors such as under-screen fingerprint sensor in mobile devices and small capacitive fingerprint sensors were not investigated. And we also would like to investigate fingerprint quality and different control mappings and different applications in our future study. Thank you.